Neural dust, the future of brain-computer interfaces. What if our thoughts could be monitored one neuron at a time? From electric eels to MRI machines, we've always used indirect signals to peek inside the brain. But could a swarm of microscopic sensors become our window into neural chatter? This is the promise of neural dust. Tiny wireless motes that drift through brain tissue, listening to the very pulses of thought itself. Early brain-computer interfaces relied on EEG, placing electrodes on the scalp to measure large-scale electrical rhythms. The signal is clear but blurred, like listening to a symphony from outside the concert hall. Moving inside, electrocorticography, EKG, lays grids directly on the cortex, boosting resolution at the cost of open brain surgery. Deep brain stimulators use wires threaded deep into neural circuits to treat Parkinson's. Yet those rigid cables tether patients to bulky hardware. Why must we choose between bulky wires and blurred signals when we crave both precision and freedom? Imagine sensors no larger than a grain of sand, each containing a piezoelectric crystal and microscopic electrodes. First introduced by UC Berkeley researchers in 2016, these neural dust motes float freely in the brain's extracellular matrix, the gel-like network between neurons. Each mote can independently record local voltage fluctuations, creating a cloud of wireless listeners. What if sensors could drift like stars in a neural galaxy, capturing the whispers of individual neurons? Neural dust motes harvest power from ultrasonic waves beamed in by an external transducer. When sound waves hit the piezoelectric crystal inside each mote, they generate a tiny electrical current, enough to run onboard electrodes that measure neural voltages. To send data back, the mote modulates how it reflects ultrasound, a process called backscatter. Variations in reflection encode the recorded signals. The transducer then listens for these modulated echoes, demodulates them, and reconstructs the neuron's activity. Could sound waves unlock the silent conversations inside our skulls? Here, the piezoelectric effect transforms mechanical pressure into electricity. And backscatter lets us hear through echoes rather than wires. Neural dust could revolutionize prosthetics by wirelessly translating motor cortex signals into limb movements. Imagine controlling a robotic arm simply by thinking. In epilepsy, motes could detect the earliest seizure signatures and trigger localized drug release before convulsions begin. Researchers envision mapping memory formation in real time, revealing how we learn languages or form lasting impressions. How might our relationship with machines deepen when thoughts become commands and therapies adapt on the fly? Yet the road ahead is steep. Biocompatibility issues arise as foreign motes can trigger scarring or an immune response that degrades signals over time. Continuous ultrasound raises concerns about tissue heating. Brain data is the most intimate form of information. How do we safeguard against hacking, surveillance, or malicious manipulation? Do we risk our mental privacy if every thought could be intercepted? If you're as fascinated by these possibilities as I am, hit like and subscribe to join us on this journey into the mind's frontier. Neural dust stands at the intersection of neuroscience, engineering, and ethics. It may transform medicine, communication, and even our sense of self, but only if we choose wisely. As we stand on the cusp of merging mind and machine, what kind of future will you envision?